like sour wine bird reservation in California.
A bird reservation?
I love
It's a
birds.
reservation.
Is that your family?
Well, I mean, apparently I'm related to this guy, but I've never met him, and there's only one person here that lives, that's part of our family, which is really weird because.
Is that by like Stillwater?
Yeah.
Okay.
Here's one. You know, in this town, there's another Jake Hall. I only represent 50% of the Jake Halls in this town. This is a pretty small town. Pretty amazing.
That's amazing.
Did the purchase like just go through like recently or how long?
Yes.
I don't know. I barely skimmed the article.
Are you on Onyx?
Yeah, I was gonna see like how much it actually calculated out because there's a lot of warehouser land over there that he could have bought. And yeah,
Well, just don't walk in his trees. Those are his. That's their property. Okay. If you step on a caterpillar, you're gonna get sued because that's his property. That's his caterpillar. Birdies?
It's like a glacier.
Yes, property. Okay.
Mr. Hall, think about this. He has so much land. He can literally have a 60-acre, like 600,000 acre fire up within his property, and it won't even touch any of our paths. Or 60,000.
Well, sounds awesome to me. Let's talk about some momentums. Momentums. So, let's talk a little bit about center of mass. So 7, hopefully, I briefly talked about this yesterday, right? Like, if you have a force versus time graph, you go, well, what's the area under this curve gonna represent? Well, the change in momentum is gonna be equal to, now this is basically gonna be the average force. But so this idea that the change in momentum is equal to the force times the time tells me that the area under this curve, this area is going to be telling us the change in momentum. Okay? Make sense? Okay, so then, so that means basically B is going to be the most directly findable thing here, or part B. So let's do the math here. What's the base of this triangle? 6 milliseconds, right? So the time is, the area is going to be 1/2 times the base. The base is 0.006 seconds. That make sense? Yes, 6 milliseconds. And then the height of the triangle is 5 kilonewtons. So that's 5,000 newtons. Makes sense? I think that works out to 15.
Yeah.
And what are the units? Since we turned everything into seconds and newtons, you could say Newton seconds. Certainly nothing wrong with saying Newton seconds. Or a Newton second is also a kilogram meter per second. Any questions on that, the units? Yes?
Do you want us to write those out every time?
If it's like the final answer to the question, then yes.
Okay.
But if it's like an intermediate step you're doing, then just make sure everything's in kilograms and seconds and meters, and then everything would work out into the correct SI unit. Okay, so now let's get the average force, right? So we just calculated the impulse from the diagram, so that's gonna be 15 Newton seconds. And then here's the force, and how much time was the entire event? 0.006 seconds. So this is gonna be, think about the units, Newton seconds divided by seconds will give you with newtons, which is what we want. And that's gonna be, that's gonna be 2,500.
So that's A, right?
That would be the answer to A. Do you notice anything about that number that's sort of noteworthy? If you look at the graph.
Yeah. Half of the.
Boom. Yeah, because the graph changes in a linear fashion. Yeah, I mean, you gotta be careful with this kind of assumption. It's kind of, you guys remember way back when we did kinematics? Colin, can you put that away, please? In kinematics, it was like, if you accelerated from some speed up to some other speed, the average speed was halfway, if it was a linear change. The same thing is kind of happening here. Since the force is changing linearly, the average force ends up being half. And the same thing is true on the sort of descent here, it's halfway. Okay, let's get the ball's speed after it leaves the bat. So this part is gonna be involving the rest of the numbers up here, because you might have been going, well, we did all this stuff, we did part A and B, we never used the mass of the baseball, we never used the initial speed, so where does that come into play? So for part C, what formula do you think we're gonna start with? Yep, P equals, so the definition of momentum. The momentum is the mass times the velocity, which means that the change in momentum is equal to the mass times the change in velocity. Now here's where we're gonna have to be really super duper careful about negatives and positives, okay? So, did we already calculate this, the impulse? 15. The mass is 0.2. That's given to us in the problem. And so, that's 75. I think that's right. Please, yeah, I think that should be right. Okay, moment of truth here. Who's feeling brave? Who wants to say what they think the answer is going to be to what's the speed of the ball after it leaves the bat? What?
It's gonna sound like with like years per second or something like that.
That's a good thing to bring up, though. Okay, the question's asking what's the ball's speed? So what do the units have to be? Meters per second. What are the units of this? A delta V. What are the units of delta V? Meters per second, right? Talking about the change in velocity. Come on, someone's got to be brave. What are the final answer?
62.
62. I like how you're thinking negative, though, because the bat, right, hit the ball in the opposite direction from when it was traveled. So the answer, is 62. So let's see, why is that? Well, the ball, if we read this carefully, it says the ball is traveling to the right at 13 meters per second. But what direction does the bat hit the ball? This way, left. So the change in velocity, really, we should think of this as a negative number, right? Because it points this way. Does that make sense? Sure. So, the change in velocity is basically in this direction with a magnitude of 75. So the net effect of that is basically 13 minus 75. So the answer to this question is 62. Are we okay with that? Yes.
Would it be okay to write those negative numbers?
Yeah. So if we want to get really technical with our negatives, maybe this should have been a negative number, right? So we're talking about the force pointing this way. If we're calling this the negative direction, then this force you could think of as being a negative value, which would make delta P a negative value. Make sense?
Yep.
We want to just do one more, just to make sure we understand it. By the way, last one quick remark here. What if somehow the ball was traveling to the right and then the bat came up from behind it and hit it in the same direction it was already going and somehow still generated this force diagram? You'd have to swing it harder to do that, but say that happened, then what would the answer have been? 88, right? Now granted, you'd have to swing the bat harder because to get this same force generation, a lot of this force comes from the fact that the ball was traveling in the opposite direction as the bat, which if you've ever played baseball, right? The harder the pitch, the more you're gonna feel that swing, as opposed to just putting it on the T-ball. I'm more of a T-ball guy myself. That's how I like to play. Okay, let's do one more and then just have like a work day for the rest of the class. Okay, we have some time. That's good. Let's do 8 together.
I played until junior high.
A 100 kilogram block is sliding across a flat frictionless surface.
We peaked, okay? We peaked really hard. I remember that. Yeah.
Okay, so for 8, why don't you guys try this yourself? I think if you're still a little confused, that's okay. Don't worry, but try the same process as before. Just keep in mind the block is, so here's the block. He's sliding to the right at 10 meters per second. And then the force, it runs into a net, which exerts a leftward force. So the force is to the left, which means the impulse, the change in momentum, points to the left. Just take a couple minutes and see what you get. We'll compare answers. here's sort of the starting point. If anyone's stuck, probably be to look at question B again. B could be your first step. Already done, Cooper? You're thinking? Doesn't look like it.
There's always one of them.
All right, so our impulse is 1,200 for units. We can say Newton seconds, or we can say kilogram meters per second. Okay, that's part B, the impulse. So just for vocabulary purposes, just remember that impulse just means the change in momentum. Now, again, like if you want to be a real stickler about positives and negatives, and you want to call this the positive direction, then you probably ought to call this the negative direction. So anyway, A. What's the average force then? Well, change in momentum is the average force times the time period. So this is 1,200. And the time was 4. So what you guys got?
Yeah.
You okay, Kate? You gonna make it? Need some coffee? Okay. All right, so then the final speed and direction. Let me show you an alternate. It's the exact same approach, just slightly different looking, and you guys let me know if it is confusing. But what if I did it this way? What if I thought, well, my block, how much momentum does my block have originally? If it's going 10 meters per second and the mass is 100 kilograms. How much momentum is that? 1,000, you just multiply those numbers, right? And then the change in momentum was 1,200, but keep in mind, it's in the opposite direction, right?
Yeah.
So what's the final momentum have to be then?
Negative 200.
Negative 200. Is everyone okay with that? The difference between these is 1,200. Well, if I know the final momentum, I can solve for the velocity, right? Because I can do this. Mass times velocity equals momentum. Does that make sense? So is this what everyone got? Did you get 2 meters per second? Going left? No?
Well, I put it as negative.
That's okay. Yeah, that's fine. To ask, yeah, what's the speed and direction? So, I mean, again, if you want to be really technical, I guess speed should be a positive number. But by the way, here, just last little remark here would be, what if I did this the exact same way we did the previous problem? How does that look? It looks pretty much the same. You would just go, change in momentum is equal to mass times the change in velocity. This number we said was 1,200. The mass is 100. And so you get a delta V of 12. And then you say, well, he was going 10, and then the delta V is 12, so that leaves him with left over 2 meters per second in the opposite direction. Right? So,
Yeah.
So those are totally equivalent methods. There's nothing different between them really. It's just here I'm kind of solving for P and then getting V, whereas this one I'm solving for the delta V and adding it up. Okay, let's take the rest of the class and just try your best to finish up through 13. And tomorrow we'll talk about center of mass.